This is our final project. We're going to do a hydrometeorology exploration of the April 19th, 2020 Southeast U.S. floods. So, flooding in the Southeast is common due to the area's vulnerability to thunderstorms, tropical storms, and hurricanes. Looking at literature and also looking at past events, we notice that widespread flooding from thunderstorms often coincides with widespread risk of severe weather. And this can be seen when looking back at the 2011 super outbreak, or even the previous week before this event, April 12th, when there was a wide risk of severe weather. Flooding also occurred. So we'll be exploring the synoptic and mesoscale setup for the event, and we'll be exploring how the atmosphere and the land contributed to widespread flooding across the Southeast. So before April 19th, at the end of 2019 and the beginning of 2020, the Southeast was already experiencing a lot of precipitation, and this was causing soil to be nearly saturated, with some areas in the Southeast being in the 95th or 99th percentile for soil moisture. Also, widespread across the Southeast, many areas had already received 130% or more of their normal precipitation for a January through April time period.
So taking a look at what happened on the day of April 19th, we're going to be doing a bit of an event analysis to analyze the specific hydrometeorological processes on the synoptic and mesoscales, as well as down to the storm scale, looking at storm orientation to understand why certain areas in the Southeast received quite heavy rainfall on the day of April 19th. As you can see from my beautiful 4-image plot going on here, we're going to be looking at the 500 millibar environment, not the 500 millibar, the entire upper air environment. 500 millibars is just what we're looking at there. We're going to be looking at some upper air soundings, surface analyses that I conducted myself with my very own colored pencils, very exciting stuff, and also some radar analysis. So we took some radar screenshots, and we're going to do a little bit of analysis of storm scale processes based on that. So taking a look at upper air observations, we will start at 500 millibars, like I said before. This is the morning of April 19, 2020, and then this is the evening of April 19, 2020, the Automated Storm Prediction Center analysis. And the first thing that can really be noticed when looking at this upper air environment is that it's dominated by this long wave trough across most of the United States, kind of this trough based up in the Hudson Bay region. And we have a fairly seasonally strong height gradient going on across most of the United States, and generally zonal flow embedded within that long wave trough. The main exception to that we're going to be looking at is this shortwave trough down in the Rio Grande Valley and Permian Basin region at 12Z. That is kind of coinciding with a belt of stronger west-southwesterlies, and the trough eventually throughout the day moved to the east, and that shortwave trough was now over the Arklatex region with, again, pretty strong west-southwesterlies. So we have kind of this large-scale forcing mechanism by this shortwave trough and strong deep layer shear promoted by the winds associated with that trough. So taking a look at 850 millibar observations, these are both from the morning of April 19, and I think they illustrate a really important feature. That shortwave trough at 500 millibars was kind of located around here. We can see an 850 millibar open wave. The Storm Prediction Center automated analysis did not close off a low at 850, but it has this open wave kind of traveling through the high plains region, what I like to call God's country of northwest Oklahoma, the northeast Texas panhandle, kind of somewhere in there. We have this open wave. And then to its southeast, we have this fairly modest 30 to 40 knot veered low-level jet bringing in kind of this veered moisture transport. We can really see the dry line set up across the West Texas plains, and then east of that, really strong moisture, deep layer moisture. And that veered low-level jet is going to be really important for storm scale propagation later on. So remember that. And then we also did a streamline analysis that kind of shows the same thing. not necessarily your typical moisture return trajectories, but these streamlines do tend to tell us that we have generally west southwesterlies at 850. So now that we've looked at the upper air environment, we can go ahead and take a look at soundings. We'll see if those can get popped up here. The first one we're going to look at is from Tallahassee, Florida, at 12Z on the morning of April 19th. First thing that really jumps out to me is that there's a modest veering wind profile. Not your crazy sickle-shaped hodograph that maybe we associate with deep convection sometimes, but a modest veering wind profile that is associated with warm air advection. So that's going to generally be important to first of all, the continued return of high-quality moisture and buoyant air into the storm zone for later on, but also as an initiation mechanism for deep convection. Looking over at the thermodynamic profile, we can see really a deep moist profile. This is a very tropical type sounding, all the way up to 500 millibars. That's a really deep moisture profile, and that shows up in the precipitable water up to 1.45 inches. That's in the 90th percentile climatologically. So not just deep moisture, climatologically more than you would expect for Tallahassee this time of year. Jumping ahead to the Lake Charles sounding. We can see that, again, we have this veering wind profile, maybe a bit more pronounced veering in the low levels, kind of shows up in the hodograph there. So again, warm air advection going on across the deep south on the morning of April 19th. Solid moisture also shows up here, not quite as saturated as the Tallahassee sounding, but the Tallahassee sounding was also a little bit cooler. So you do tend to have similar mixing ratios in the surface to 500 millibar layer. So again, a pretty strong precipitable water value of 1.37 inches showed up at Lake Charles. And then the other really important thing to look at are these steep mid-level lapse rates. So it appears that there was actually a little bit of an elevated mixed layer that advected into the Lake Charles sounding. And so we have a ton of most unstable CAPE, 3,500 MU CAPE at 7 a.m. So lots of convectively available potential energy for storms to tap into when they eventually formed over the deep south. We're going to look at one final sounding. It's from Jackson, Mississippi, and it's actually a special midday sounding at 17Z. The veering wind profile is a little bit harder to tell here. Kind of have that classic hodograph look, but actually at the surface we have a northerly wind observation. And that's because Jackson at the time, as we'll take a look at in just a moment, was just north of the surface warm front. So what that meant was that we have surface northerlies that very quickly shifted to southeasterlies and then a veering wind profile above that. So there is warm air advection aloft. It's just a little bit hard to tell because we're kind of right in the frontal zone. And that front actually shows up right here with this little inversion at the surface in Jackson. That's the last remnants of the frontal inversion that we tend to see when we're looking at cross sections of warm fronts. So that kind of shows that there's a fair amount of MU CAPE, but all that CAPE was eventually about to rise after frontal passage. I believe the observation at 18Z for Jackson was 75 degrees with a 75 dew point. So really rapid jump in the buoyancy, and I believe I put the sounding into, or I had someone on Twitter put the sounding into Sharp Eye for me, and that comes out to 3,500 CAPE. So the instability was there at Jackson. It was just a little bit north of the front at the time. Moving ahead to surface analysis. This is the real fun one. I spent most of the day on April 19th coloring in my surface analyses. I was very excited about it. The green shading denotes areas of higher moisture. So down here in this dark green, that's 70 Fahrenheit. Right here in this bluish green, that's 65. And then this lighter green is 60 or higher. So we can kind of see through that moisture gradient, there is a warm front draped across the deep south, and it runs basically from East Texas all the way off the Atlantic coast. And also the blue lines just above the outflow boundary over Georgia and Alabama denote an outflow boundary from earlier convection. So that's going to become really important. First of all, there was an early round of convection in an area that was about to receive heavy rainfall later on, but also that outflow boundary was sagging southwards and eventually influenced the warm front and both strengthened the temperature gradient and increased surface wind convergence across the area. We can take a look at that actually right after this when we go to the 18Z surface analysis. The warm front, as you can see, there's a line south of the warm front. That's where the warm front was at 15Z. So the warm front really advanced through central Mississippi and actually went past Jackson. But the warm front didn't move as much over Georgia or Alabama because the outflow boundary collided with it. And this created significant surface convergence. It really sharpened the temperature gradient across the area and the moisture gradient and became a key mechanism for storm initiation over eastern Alabama and western Georgia in the areas that ultimately ended up receiving the highest amounts of rain. You'll also note that in orange, I denoted areas with dew point depressions over 10. That shows pockets of sunshine, basically, where the sun had come out south of the warm front, which added to the instability profile south of the warm front and provided further juice, basically, for all this severe convection. I'm going to pass it back over to Josh now for radar analysis.
Okay. So from radar shots from that day, we noticed that MCSs did form, and then they took a significant east to west orientation, and this was probably due to the veer in the low-level jet at the time. There was also low-level sear, and and the storms became parallel to that. And over time, this caused a parallel but opposite direction in storm motion and storm propagation as new storms developed. This caused storms to become training and cause heavy precipitation to fall in the same area over and over for a few hours. But there was also a lot of high bulk shear as well, and this allowed for organized supercells and squall lines as well. And so this radar image here shows looks like a high P supercell. You can see the velocity indicating the mesocyclone. And this just allowed, and so with intense updrafts, you also allowed for heavy precipitation and also with the rotation, side sorting of particles as well.
So the Weather Prediction Center issued a moderate risk for excessive rainfall the morning of this particular event from eastern Louisiana all the way to western South Carolina along a pretty narrow corridor that included central Mississippi, central Alabama, and central Georgia. There was the expectation of a large swath of 2 to 6 inches of rain within 24 hours over these areas. And there was definitely the potential that we could see over 6 inches of rain within a very short period of time in some of these areas and localized areas outlined here within these two graphics. Moving on to kind of the more notable mesoscale discussions. So the morning of, there were a couple of mesoscale discussions that were issued. One of those being for that morning convection that was previously mentioned. There was some concern with the lower level jet advecting a lot of moisture into northern Mississippi and northern Alabama, that a lot of the training convection that was already present they were going to be seeing some enhanced rainfall rates from more efficient precipitation. And so this caused some pretty heavy rainfall rates across northern Mississippi, northern Alabama, the morning of this particular event. And it really saturated the soils in advance of the convection that was going to be there later that afternoon. And a similar story for later that morning across central Mississippi and central Georgia, where that outflow boundary was really sagging. There was a lot of training convection once again, with more moisture advection in this area, leading to more efficient rainfall rates. And it really set up a situation for whenever those afternoon storms came into this area, they were going to be training over these areas that already saw saturated soils and had already seen quite a bit of rainfall, including some flash flooding, especially in central Alabama and Birmingham and Montgomery. And then we go on to kind of our evening mesoscale discussions, where it's pretty much a lot of the same story, where we're talking about training intense convection across these areas. The one on the left pertains to that supercell that we saw earlier across southern Mississippi, where we had an extremely intense supercell that actually produced a violent tornado. And then we had training convection behind that causing quite a bit of flooding across southern Mississippi. And then once again, across southern Alabama and southwestern Georgia, that outflow boundary sat in the same area. We had a very intense low-level jet with all that moisture convergence, and we had some very efficient rainfall rates in that area that ultimately produced some pretty significant flooding. Now, we kind of want to go over some of the overall impacts across the Southeast, where a lot of the Southeast saw 3 to 5 inches of rain, once again from Louisiana to South Carolina. But there was a pretty narrow corridor there in central Mississippi and central Georgia where they saw 5 to 8 inches of rain, once again, likely in association with that sagging outflow boundary and the moisture convergence there. Kind of going and looking at a more close-up view, we're going to move on to some of the impacts they saw in Mississippi from this particular event. There you can see on the top picture that supercell, that very intense supercell south of Hattiesburg that was producing some incredible rainfall rates, at least 3 inches per hour in some of these areas. And then it started to backbuild, and we saw vigorous convection training over the exact same areas that produced incredible amounts of rainfall in a very short period of time. And this ended up causing a lot of issues, especially with travel. There were several cars that ended up trapped in floodwaters and several people that actually needed water rescues. And the Hattiesburg Police Department ended up having to close US 49 for the night because of the high water. And we can see there, that picture on the bottom, how high that water was underneath this overpass. Going into Alabama, they experienced a lot of the same conditions where we saw a ton of flooding in Montgomery and Birmingham, very populated cities within this state. Essentially, they were under flash flood and flood warnings throughout the duration of the event, just simply because of how long that they were receiving rainfall throughout the day. And then there were multiple roads in Alabama, particularly back roads, where we saw kind of some weaker infrastructure that ended up getting washed out by creeks that had swollen and overtopped their banks and ended up washing out roads, which made it difficult for any kind of first responders or any kind of emergency management personnel to get to some of the rural communities that that were impacted by this particular event. Georgia, it was a lot of the same story once again. A lot of flash flooding because of the efficient rainfall rates that occurred in very populated cities, particularly Columbus, Georgia, where the Chattahoochee River ended up cresting in minor flood stage, but this actually caused pretty significant flooding within downtown Columbus, Georgia, where their Riverwalk section was flooded out for quite a number of days because of this event. In fact, Columbus, Georgia saw their second highest daily rainfall total that they had ever seen from this particular event, almost 6 inches of rain in 24 hours. And downstream effects are actually still being felt in southern Georgia as well, as all of this water that fell over central Georgia and central Alabama is currently flowing towards the Gulf of Mexico and the Atlantic Ocean, and they're seeing some pretty significant river flooding in southern Georgia as we speak. Now, places like Louisiana and South Carolina, while they didn't necessarily see the highest impacts, they did still see some impacts. There were some places in South Carolina and Louisiana that did experience some flash flooding, although definitely not as significant as we saw in Mississippi, Alabama, and Georgia. However, there are places in Louisiana that are feeling some of the downstream effects from this event and the events prior. In fact, the Mississippi River in Baton Rouge, Louisiana, was at major flood stage as of April 25th. Now, while the water levels are decreasing, this is still creating some pretty significant impacts along the Mississippi River. And there are numerous rivers and creeks that are in minor and moderate flood stage that are causing some impacts in some nearby communities from this particular event.
Okay. So in conclusion, quoting Jeff Becerra, this case was an excellent bridge between the synoptic, mesoscale, and hydrometeorology. Land surfaces were already pretty saturated, and rivers were already higher than normal for the time period. And when coupled with synoptic pattern allowing for great moisture return and a great depth of moisture, and mesoscale allowing the strengthening of the convergence zone along the front that allowed for convection and try to form precipitous form over a large area over and over, contributed to flooding across the southeast. And this all resulted in washed out roads and danger to life and property in Mississippi, Alabama, Louisiana, Georgia, and South Carolina.
I think this pretty much concludes our presentation. Thank you for listening. We've really enjoyed learning more about the bridge between the atmosphere and the land and how mesoscale and synoptic processes can influence hydrometeorological processes. Thank you and have a great day.